Hi everyone, welcome. So first let me introduce myself. I'm Chenyan Xiong. I'm a researcher in Microsoft Research. And in this talk, I will talk about my recent research and also my visions, findings, observations, and also prediction of futures in dense retrieval, which many of us view as a new paradigm of search. So I put three terms in the title. I call it progress, capability, and challenge. So that's also how I organize this talk. So first, what is dense retrieval? Many of you may have heard it or maybe in previous talks, but here I want to give my formal definition, my personal definition of dense retrieval. So I call dense retrieval to cover all the technique that performs information retrieval by first encode the query and documents or any user information and the data into a dense representation space. For example, passing through some neural network encoder and to get some embeddings of the query and document, and then performs the retrieval by giving a query and find its relevant documents or use for information using k-nearest neighbor search purely in the embedding space. So then the term dense here is really in contrast with the classical retrieval, which everything is done in the sparse representation space, where the query is represented by, for example, some backwards sparse vector, documents is done by some sparse backwards vector, and the match is done in that sparse space. So how the data is embedded and represented is where it makes the difference between sparse retrieval and dense retrieval. So in the past 2 years, I think, there has been a wide adaptations of dense retrieval across many information access scenarios. So here I list some scenarios I personally have tried dense retrieval in. They will include the call search, where the goal is to give a user queries to find relevant documents from the whole, for example, the whole entire web corpus. And also include open domain question answering, where the goal is given a user's natural language question to answer that question. But to answer that question, you need to first find evidence documents that contain the information needed for that query, for the question. And the third one that I have tried it on is content-based recommendation, where, for example, you're given a set of documents that user previously have viewed or liked, for example, news articles. And then we can use dense retrievals to retrieve all the related documents that match user interest as she has shown in before. And also in conversational systems, we can also, by using the dense retrievals to match users' information need by inferring from the user conversation with the system, and then to use that embeddings of user interest to retrieve relevant documents that the system could use to respond to the user. So here I gather some empirical comparisons between purely dense embedding-based solutions with the sparse solutions, like classical sparse solutions, including BM25, TF-IDF, and also learned BM25 using BERT, etc. So you can see that across many different tasks in different domains and scenarios, we are able to achieve, for example, relatively 10-point or even 20-point relative gains by switching to a purely dense embedding-based solution. So what leads to this progress? What makes the dense retrieval so powerful in these scenarios? So I summarize the key technique contributions in two parts. The first one is pretraining. So I call it as the BERT advantage. We're given a very deep neural network. We can first pre-train the deep network using language modeling tasks, for example, in a very large scale corpus, the entire Wikipedia or the billions of web documents, and in a way that is a pre-trained neural network, for example, a transformer-based model, will be able to capture some basic language semantics. And then that provides a very good starting point for your dense retrieval model. And then if you fine-tune, like continuously train these pre-trained transformer models on your dense retrieval task, then that leads to really good performance. And the second one is more on the fine-tuning stage, that people have started to figure out the best ways to fine-tune or better ways to fine-tune this pre-trained model in the dense retrieval task, where one of the key is where I call it a noise contrastive learning, to capture in a way that it's all about how you pick the data in the embedding spaces, in the embedding space as your training example. For example, given this dimension reduction using TSNE or this representation space for the query, the relevant documents that you want to really retrieve, and all the negatives. So a lot of studies has been done about how to pick the other data points in this entire space as a negative training examples. So we know that if you pick the random ones here in this space, it will be very trivial, and the model will be not really learn to push for the best dense retrieval performance. But if you, by mining the negatives, the hard negatives, for example, using a sparse retrieval system, or dynamically using your current dense retrieval model, that really leads to a very good downstream performance in the dense retrieval tasks. And also, furthermore, in terms of capability, I also found it very encouraging that using this deep representation space, we actually can perform more complex tasks, where it's not about, say, shallow similarity, where this query and documents may talk about similar things and we just pull it from the entire corpus. But actually, by using this high-dimensional learned dense representation space and solely by cosine similarity, we are actually able to do some more, say, semantic and reasoning tasks. So use this multi-hop question answering as one example, where the task is that for the user still give you a natural language question. The difference is that this question is more complex, that it needs information from multiple documents altogether and perform some reasonings like induction, etc., to compose information together to find the final answer. Traditionally, this often requires some symbolic solution, require something like semantic parsing, or require some back-end knowledge graph to really answer this type of question. With dense retrieval, what we found very interesting is that we actually can, by using this embedding space, by first, for example, giving the question and find the first paragraph using one dense retrieval, embedding and cosine similarity. Then we can combine this query and some partial evidence altogether, do some compositions and find a new query embedding, and then use these new query embeddings to find the next document or passage needed in this evidence chain. And this embedding space you can consider as you can start from here in the first query, and you do a first hop to find the near passages which may contain useful information to answer this complicated question. And then you can do a composition of the two together and as a traverse or hop in this space for your second hop. And then you can repeat this progress to really traverse through these virtual evidence chains and do some more complicated reasoning stuff, purely using embedding, composition, and cosine similarity. And one bonus is that we also found that you may not need any annotations in this evidence space. You don't need any passage level or document level annotations. You can directly start from the query using the answer as a final goal, as your North Star in your reasoning process, and perform this composition and traversing in this embedding space and reach there. So with all the progress and capacity in mind, there are also some challenges we have recently observed. One of the big challenge is a mismatch between the performance of pre-trained model on more like standard NLP tasks, which these pre-trained models are mainly developed for, and also their performance on dense retrieval scenarios. So here is I put three famous common widely used pre-trained model, BERT, Robot, and Electra as an example. So you can see that on a standard glue task, on the squad reading comprehension QA task, the newer model of course does perform better than an older model. But if we measure this model on dense retrieval tasks, where it's shorter text or longer text, we can see a reverse trend in comparison with their performance on more standard natural language processing tasks. So why that's a mismatch is still unclear why. But here are some popular assumptions. One assumption is that there may be some discrepancy between what is needed for modeling language, like to predict what is the missing token, in comparison to what is needed to model, say, the dense retrieval, the relevance or user interest between a query and document, etc. And also in the pre-training part, technical-wise, there's really no specific pre-training task to emphasize a better, say, document embedding. All the pre-training tasks, like in this model, are about to model the token level information. So there is also a mismatch in how the model is pre-trained and then how it is needs to be used. One potential direction is to do more retrieval-oriented pre-training. For example, I list one quick exploration that we have done in this year, where we use auto-encoder model that we stack a decoder on top of the BERT-style encoder, and using the decoders to form the information bottleneck in the sequence encodings and to really push for a very good sequence encoding. And we have a lot of observations that if we make this decoder very weak, very shallow, like 3 layers, and also attention span, maybe only each position can only see 1 or 2 tokens, it actually leads to a better encoding and leads to better dense retrieval performance. So last but not least, I want to list 4 my quick predictions of the future trends. The first one is that we believe that dense retrieval is going to roll out in the search industry. It will be more and more important in both data-rich setting and unsupervised scenarios. And then we also believe that it could be more unified tech stack and more universal representations across different information retrieval scenarios and also different data formats. And last but not least, I would say that this really provides us opportunity that is semantic search for everyone, that we can provide the techniques through the open source solutions, public available training models, and also push button cloud API calls that we can share this best technique from search engine companies and to all over the world, all the customers, all the users, etc.